and we start share screen. Good. So our usual lovely table. And I can't stress enough, if you have any questions, stop me anytime. Where is the basic tools, snapshot? All right. We need this table in the back of our background to be always in the background. It's very important. Without it, we'll not be able to talk. All right. And to prove to you that it's really a general discussion, let's take an example in real experiment, aside from the course. So the example that I always like, which is we have a wind tunnel section. So this is the wall of the wind tunnel, the upper wall. And here is your wind tunnel model, inclined. Oops, no, that's good enough. Okay, and we have, so this is the wing. So this is X body. This is Z body. So can you tell me what angle is this? What angle is that?
Alpha.
I did not draw the velocity vector. If the velocity vector, yeah, so this is now, exactly, this is just the body. So this is indeed theta. Okay, is it? Yeah, it's okay. So this is theta, but as you guys expected, if this is a wind tunnel and the flow is coming horizontally, this is U or V. What do we call it here? We call it V. That's fine. So so in this case, this is also the angle of attack alpha. That's fine. And here is the other side of the wind tunnel. The airplane is free to pitch here around the CG. So this is a hinge that allows the airplane to freely rotate about the CG. So it doesn't move in any other direction. And please recall your MAE identity, the dynamics. Just I could really have this problem in the dynamics class. What is the equation of motion? Let's see, what's the question? This is not Q, right? Q is this is a very good point, Ibrahim. I don't know if you're referring to the angle, but if you, yes, it's a very good point. Q, we're coming back to it in a minute. Q is the velocity, not the position. So the position, we call it theta, and Q is the velocity, the angular velocity. Let's write down the equation of motion in an MAE 80 setting. Just basic, simple, forget what you learned in this class. Please, I'm giving you a body that has 1 degree of freedom, rotational degree of freedom, theta. What is the equation of motion? Well, the equation of motion from MAE 80 is I theta double dot equals the torque, correct? And in our language, let's be a little bit more professional. Well, in our language, this will be my I is actually IY, because this is about the y-axis. I know that we have 3 principal moment of inertia of the airplane, X, Y, and Z. So this is about Y, because it's into the page Y, right? And it's theta double dot equals the torque here. Well, what are the forces? I have force of gravity, but it's passing through the CG, it doesn't create any moment. And I have a reaction force from the hinge, but the hinge is at the CG as well. So again, no moment. So the entire moment or torque is coming from aerodynamics. and it's the pitching moment M, what we call it M, right? Because we have 3 moments. Look at this guy here, LMN. We're doing the rotation about Y, so this is really what we call M. Any question about this black equation? IY theta double dot equals M. And like anything in this class, I'm gonna expand M as a value at the operating point balance plus delta M, right? Change from the operating point. Fine. Then I will assume balance at the beginning. So I will assume M naught to be 0. Assume that the airplane was balanced at the beginning. So my equation of motion now is simply theta double dot equals, again, folks, please, if you didn't study anything, just start fresh here and stop me anytime. This is really a general discussion. We're starting from a concept that is basic, MAE 80, that you have seen 2 years ago. Okay, so now from this class, I will borrow delta M over IY. From this class, we just learned it the last lecture and the lecture before, that I can write this as here where you need the knowledge from the last 2 lectures. If you didn't study, that's fine. You can just believe me that you can write this delta M over IY as MU delta U, MW delta W, MQ delta Q. Well, whatever M depends on, you're gonna keep adding things. M elevator delta elevator, M thrust delta thrust, right? This is the things that we decided pitching moment M will depend upon. So there is actually an elevator here. This is the tail, and this is the elevator that we can move up and down. All right. But this is in general in free flight. This is the most general expression for the delta M, the change in pitching moment from operating point like cruise or something. We are in the wind tunnel, so things will, some things will go away. Like what? Like no thrust. I'm not playing with the engine at the wind tunnel. And the speed is fixed at the wind tunnel. These are zeros. Okay, what else? I also have, what can you tell me anything about W? Yeah, of course, we always know that delta W is indeed U naught times delta alpha. We always said that delta W, or W is nothing but the angle of attack. Whenever someone mentioned W in front of you, this is really angle of attack, okay? It's simply a constant multiple times the angle of attack. The U naught, this speed, multiplying by the angle of attack. All right, so I can really replace this MW delta W. I can write it MW delta W or M alpha times delta alpha. Because what is the meaning of MW delta W? Is the change in pitching moment divided by IY, that's fine. The change in pitching moment due to changing in W. We just said that the change in W is equivalent to change in the angle of attack. So I will write it like this. M alpha delta alpha. So this is the changing in M due to changes in alpha. All right. Any question about this replacement of MW delta W by M alpha delta alpha? Okay, what else? I have, can you tell me what is Q or delta Q in this scenario? What is Q? Let me choose a good color here, this one. Can anyone tell me what is Q?
A small pitch disturbance? Or is it?
Yes, yes, but what is its meaning? What do you mean by Q?
There's been a change in the angular velocity.
Exactly, it's the angular velocity, right? So it is the angular velocity. Okay. Can we relate it to anything here? What about writing Q as theta dot simply? Anybody doesn't agree? I mean, this is angle and this is angular velocity. So this is the rate of change of that. All right, so this is good. So let me now collect all what we had so far. So theta double dot from the left-hand side equal the right-hand side. The first term mu delta u goes away. Then I had M alpha delta alpha. Then I had MQ times Q, and Q is theta dot, right? Then I simply had the last term, which is M elevator delta elevator. Any question about this equation? Okay, I mean, we started with a simple equation of motion and played with some terms.
Professor?
Yes?
Sorry. Why did the delta U go away again?
Because U is the forward speed, changes in forward speed, and in the wind tunnel, the airplane doesn't move. The speed only comes from the airspeed of the wind tunnel, and it's fixed, no changes. Yep.
Perfect, thank you.
Yeah, and you guys have to tell me what is delta alpha? What's alpha in this example? Frankly speaking, alpha is simply theta. In general, they are not the same, but in this example, because the airspeed is strictly horizontal, so the angle between the body and the horizon is the same as the angle between the body and the velocity, right? So theta is alpha. Very good. So now I'm going to write the following. I'm going to summarize. My equation of motion is theta double dot. I'm going to bring this from the other side. Minus mq theta dot minus m alpha times theta equals m elevator times elevator. This is my equation of motion. Oopsies. Any question about that? Okay. Anyone sees any relation between this equation of motion, at least the left-hand side, with something common that you saw many times in your engineering classes or even high school?
Second order differential equation.
Exactly. Everything in life is a mass spring damper. Anything. This is M, K, and C. What's the equation of this guy? Well, it's mx double dot plus cx dot plus kx equal the forces, where this is the force, this is the displacement in the same direction. Correct? And I can simply divide by mass. So this is C over M, K over M, F over M. This is great. Why? Because now I really can draw the analogy. I can draw the analogy. My spring for the airplane motion is this term M alpha. My damper is this term MQ. This is super important. Now I can know what are my springs and damper. So because what is this M alpha and MQ? We have spent quite a bit of time deriving expressions for these things which really didn't have much meaning. What is MQ? We spent like 10 minutes last time deriving an expression for MQ due to horizontal tilt. But what is it? And we spent the first half of the course with M alpha and driving expression for it. What is it? They are, M alpha is your spring. K, it is really a spring. And MQ, it is really your damper. It's as if this airplane is attached to a helical spring here to the floor of the wind tunnel. Exactly. A helical spring and a helical damper. Okay? Any question about that? It's quite important. Now they become to have physical meaning. This is my spring and this is my damper. If I want to damp my motion quickly, I need to increase MQ. If I want to increase the speed of the response, because this is the speed. Why? Remember, K over M is what? Your natural frequency. So this is your natural frequency. M alpha that we spend the first half of the course with is simply your natural frequency, omega n, right? Omega n is square root K over M, right? So, and we derived the expression for these guys in terms of the airplane geometry. So you can, if you like, you can adjust the airplane geometry, in particular the horizontal tail, to adjust your spring and damper, okay? Again, this is a very important lecture. I want you guys to focus and don't let anything to pass. Don't let anything to pass simply because you didn't study. That's perfectly fine. Stop me anytime. Okay, so this is very important. And we know that in order for this system to be stable, the mass spring damper system, in order for this system to be stable, it is sufficient, and actually necessary and sufficient, that I simply have any value for K and any value for C. For any positive, just by the mere fact that you have a spring and damper, the system is stable, period. Okay, and it's necessary, which means if you remove any element, it's not stable. And sufficient, which means if you have them both, you ensured stability. Okay, so this spring and damper, in order for K to be positive, I need my M alpha to be negative, and I need here also C to be positive. MQ must be negative, and I know this from before. I know from before that M alpha must be negative. We spent quite a bit of time with this, with that C M alpha, the coefficient of M alpha must be negative. And now we're adding that the coefficient or MQ without C must be negative as well. This is my damper, this is my spring, okay? And I'm gonna add here new columns, spring action, stiffness, what we call a stiffness. And I'm gonna add damping, stiffness and damping. So in the pitching motion, what is our stiffness? Spring, it's actually M alpha, and it must be negative. Damping is MQ, and it must be negative. Okay. Any question about that? So again, these are standard names. When you go to an interview at Boeing and they ask you about pitch damping, they will not ask you about MQ. They will ask you about pitch damping. Okay. And we derived last time pitch damping. What's the main source of pitch damping? Like we derived a detailed expression for it last time. What's the main source? It was the horizontal tail. So, but by the mere fact that you have a horizontal tail here and there is an air coming, if you just push this airplane over, it will oscillate and come back naturally to its equilibrium position. It's as if you're pushing here against a spring and damper. So this is actually very interesting experiment. Again, every year I say this, that I would love to do it, but we don't get the resources and time to do it. But I mean, we have this experiment in the wind tunnel. Okay, we have an airplane in the wind tunnel, and it's hinged here at the CG, so it's free. Turn off the wind tunnel, so there is no air. No air means what? Means there is no spring and damper because the spring and damper coming from aerodynamics. So there is no air. Go and push this airplane, push it on the tail or on the nose away from the CG, give it a disturbance. What will happen? There is no spring, no damping. It will go off, nothing to restore, nothing to resist. Now turn on your wind tunnel and give it the same disturbance. It will just resist you and come back to its equilibrium position after some oscillations. Questions about that? All right.
Professor.
Yes.
Just to make sure when I go to an interview, it's called pitch stiffness or pitch spring?
Both.
Both. Okay.
Spring or stiffness.
Okay, but if I because you were saying something about an interview, and would they say pitch stiffness or pitch spring?
It depends on the interviewer. Yeah, I mean, both names are used.
All right, thank you, Professor.
Yeah, stiffness is more is more academic word. Yeah, stiffness is more common. Okay, let's see, just to remind you, what is stiffness? What is K? What is a spring? Spring is an element that gives you a force proportional to displacement, right? So if it's a translational motion, then it's proportional to the displacement x. If it's a rotational motion, it's proportional to the displacement theta. Okay, so it's a force due to displacement or a moment due to an angle. This is why here we have M alpha is my spring or stiffness. It's a moment M due to an angle alpha, and it's opposing the disturbance. Okay, so M alpha is your pitch stiffness or pitch spring. What about yaw. Can you tell me about yaw stiffness? What's the yaw stiffness? It will be a moment in due to an angle in the same direction. What would be that angle? In due to what?
It'd be beta.
Beta, exactly. So this is indeed my yaw stiffness or Weathercock stiffness. Remember the name? So this is in beta. And what about here? Will be L what?
Also beta, right?
Yes, it's also beta. Remember, we don't have a third angle. And the requirements, if you remember, we already studied this before. This is just, I mean, this is just sign convention, but the underlying physics is the same. What's the underlying physics? All of these things, they are opposing the disturbance, okay? What about damping? So this is spring or stiffness, force due to displacement. What about damping? It's a force due to velocity. It's not displacement. It's multiplying by x dot now, right? So it's a force due to velocity or a moment due to angular velocity. This is why here it's moment m due to angular velocity q in the same direction. Pitching moment due to pitching angular velocity. So this is pitch damping. So mq is my pitch damping. Look at this now and tell me what is your yaw damping?
NR.
Exactly. It's in the moment due to the corresponding angular velocity, yaw angular velocity here. So it's NR. What about roll damping? What's
LP.
roll damping?
LP.
LP, exactly. And again, we derived expressions for these guys last time. Actually, these exact three, LP, MQ, NR. The main component of MQ, I don't know if you remember or not. This is what we did last time. This was the horizontal tail, right? The main component for NR. And these are the final questions. I mean, questions in the final. So we have what? 25% of the final? 10 grades out of the 40 grades. Questions like this. What's the main component affecting yaw damping? What's the main component affecting pitch damping, and so on and so? NR was due to vertical tail, if you remember last time. LP, anybody remembers what was the main thing? Wing, right?
Dihedral?
No, this is L beta due to the dihedral, exactly. LP, these are the things that we just saw last time, last lecture, stability derivatives.
Oh, right.
Yeah. So these are damping. Remember the objectives of part 2? To account for damping in all directions. Now we managed to account for damping, really, right? We have seen these actually in the first half, and now we account for damping. Okay. So now we know our stiffness and damping in all directions. So,
Professor?
yep.
For the damping, are they all negative because we're assuming there's a positive perturbation?
Exactly. So this is natural. Why? Because they are the same sense, the same, they following the same sign convention. So we assume a positive R and get the resulting yaw moment. In order for stability and damping, it has to be opposing, of course. It must be negative. And this applies to all of them. Okay. So that's good. We identified our stiffness and damping, and we know that if I have a single degree of freedom, whether it's rotational or translational, single degree of freedom like this body in the wind tunnel, single degree of freedom, a necessary and sufficient condition for stability is just to have a stiffness and damper. So we're fine, we're done. But the issue is, in flight, we don't have a single degree of freedom. We have 6, and they interact with each other. So how can we ensure stability? If we have a single degree of freedom here, where just having stiffness and damping is sufficient. What about adding more stiffness and damping? So let me add more. I'm adding good things. I'm adding stabilizing elements, right? Stiffness and damper. This is mass 2. Another stiffness and damper. This is mass 3, or actually, let me stop here. Okay, so the black thing is just a single degree of freedom. We know for sure, just having any values of stiffness and damping, the system is stable. it will eventually come back to its equilibrium if you disturb it. Very good. Now, I added more stabilizing elements. So I added more good things. I shouldn't expect any bad thing to happen. But unfortunately, no. If we have multi-degree of freedom system, this is X2. Now we have more than 1 degree of freedom. Having stiffness and damping in all directions separately is not sufficient. And we said we discussed this before. Okay. So just here is the example. I have stiffness and damping in all directions separately, and we actually identified what's the part of the airplane that is responsible for each stiffness and damping. This was in the first half, and this was last lecture. So we have stiffness and damping in all directions separately, but they may interact with each other. They affect each other, so that the result may be unstable. I can give you here indeed a combination of K's and C's, stiffnesses and damping, such that this system is unstable. If you touch it, it blows up. Okay, so now it's not just I need to have a stiffness and damping. We need a rigorous theory, because we have 6 degree of freedom system, so it's multi-degree freedom. It's in free flight. They are interacting with each other. Roll affect yaw affect roll affects pitch non-linearly, and so on. So we need a rigorous stability theory. Any question about that? Okay, so we need a theory. So that when you give me any degree of freedom, I just plug it into the conditions of this theory and check stability. What is this theory? Well, first of all, in order to use any theory, you have to prepare your system or to represent your system in a form that is digestible by the theory, that is amenable to apply the theory tools. So how do you represent? So this is representation of linear dynamical systems. How can I represent a system like this? Well, I can represent by writing down the equations of motion, of course. That's right. But the equations of motion, they are useful, but they are not so useful in determining stability. I mean, you write the equations of motion, you can do simulation, but how can I check stability? Okay, you guys have seen the classical control theory. This is MAE 170. I hope that many of you have taken it, but if not, that's perfectly fine. We will review, actually today, we will review what we need from this theory. And okay, how do we represent in 170? How do we represent a dynamical system? Whether it's an airplane, a submarine, a car, a robot, it doesn't matter. At the end of the day, when they give you a system, in a homework or exam or whatever, and they give you, here is a dynamical system. What do they give you? They give you transfer function, if you remember. So the language that you talk in this course 170 is in terms of transfer functions. And what's transfer functions? Well, G of S is simply the Laplace transform of the output in the S domain divided by the Laplace transform of the input, actually at 0 initial conditions. Some people forget this, but it's very useful. At 0 initial conditions. Give me your transfer function, I can tell you right away if this system is stable or not. So let's do that in our example. I have the equation of motion. It was theta double dot, right? This is negative MQ theta dot negative M alpha theta equals M elevator. Okay. I need the Laplace transform of output divided by the Laplace transform of input. So let's first take the Laplace transform of this equation. Well, the Laplace transform for us here in this course is so easy. Why? Because just replace each dot with S. And actually, the fact that zero initial conditions help you in doing that. So this is like we cannot do that if we have non-zero initial conditions. So luckily we have zero initial conditions. Okay. So simply any dot you see, put S in front of it. So now theta double dot will be S squared theta in the S domain minus MQ is a constant. Theta dot will be simply S theta of S minus M alpha is a constant. Theta will be just coming out as theta of S equals M elevator of S. Okay. Any question about this last blue equation? And now we need to define what is my input and what is my output in order to do this division. So let's look at our example. What is the output here? What do you think is our output here? Anybody suggests? What's the output in this example? What can be an output? The output is usually the motion. So this will be theta. And if theta is the output, what will be the input? What is the input as a pilot or autopilot to control the airplane motion theta? What's that?
The elevator control.
Elevator, exactly. So this is elevator is my input, theta is my output. And here in this equation, just if you look at this equation, you immediately realize the usefulness of Laplace transform. Why? Because in the black equation, I had theta double dot, theta dot, and theta. They were three different animals. I could not add them together or do anything. They are really different animals. The Laplace transform transfers this differential equation into an algebraic equation. There is no dots here anymore. The theta double dot, theta, which were three different animals, now they are all the same thing. So I can add them together. So now I can take theta as a common factor and have S squared minus MQS minus M alpha. This is all multiplying the same thing. Whereas before they were three different animals. Questions? All right, this is also of S, of course. And now, like you identified, folks, the output is theta and the input is delta elevator. Of course, this is of S, this is of S, just stressing. So this is what? This is M delta elevator divided by S squared minus MQS minus M alpha. And I need you to know how to do this. In other words, whether you took 170 or not, I need you to know when you are given a differential equation like this, how to get a transfer function. So any question about these two lines? All right. So I got my transfer function, which is the language that we talk in order to make use of the tools here. So please, classical control theory, tell me how to solve this problem or to assess stability, determine stability if I have a transfer function. All right, that's easy. We have a theorem. And a theorem means it's not negotiable. Theorem means it's proved. Theorem here, M, it's not like theory, it's a theorem. Proved mathematically. It says that a transfer function is stable, and you know it very well, if and only if, when I write double F, or mathematicians when they write double F, they mean if and only if, necessary and sufficient. What? All the poles lie in the left half plane. Okay, what do you mean? We agreed that our language, everything will be in terms of the transfer function, because this is how we represent our dynamical system in this setting. Transfer function has numerator, like you see here, numerator and denominator. The poles of a transfer function, if you guys remember, the poles are simply roots, the solutions of the denominator. Right? So solve, get the denominator. So when we get the denominator, we get something called characteristic equation, right? if you remember. What's the characteristic equation? The denominator equals 0. So S squared minus MQS minus M alpha. This is 0. This is the characteristic equation. The denominator equals 0. Solve this equation to get the poles. These poles, solve it for S, of course, because MQ and M alpha are constants. Get the poles. When you get the poles, all the poles must lie in the left half plane. So if they are real, they must be negative. If they are complex, focus on the real part, it must be negative. They must be in the left half plane. Okay? Any question about that? Okay, so we need to solve this, please, to get the S's, the poles, and see where they lie in the left half plane to get conditions for stability. Luckily, if I have a second order system, like S squared plus A1S plus A2, right? So this is stable. The condition becomes if and only if A1 and A2 are stable. So the theory here, this theorem that the transfer function is stable if and only if all poles lie in the left half plane. This is generic. Give me a transfer function that's second order, third order, or ninth order. It does not matter. Solve for all your poles. They must lie in the left half plane. If you have a second order system, this condition becomes simpler. We know that if A1 and A2 are positive, actually the poles will lie in the left half plane. And in this example, if we apply this, it gives you that MQ must be negative and M alpha must be negative, which we know from before, right? We know from before because this is my spring and this is my damper, and I know that if I have just a single degree of freedom, I must have a stiffness and damping, and it's necessary and sufficient. It's if and only if. But if it's if I'm considering the entire airplane, ninth order system, 9 by 9. So ninth order system. So here I will have S to the 9. Well, I will not be able to apply this, and I will not be able to see stiffness and damping anymore, but it's fine. I have the theorem. You have S to the 9, go and solve for your S's, get the poles, they must lie in the left half plane for the stability, period. Questions about that? So we're reviewing together the 170 concepts.
I guess I had a quick question.
Please.
Are we gonna have to deal with S's on top, like any zeros or anything? Since
That's fine. They don't affect stability.
Okay.
Yeah, these are the zeros, like you said. Zeros don't affect them. Interestingly, stability depends only on the poles. Here is the theory. The theorem, I'm sorry. Only the poles. Very good. So this is now the modern control theory. As I always say, sometime the modern becomes classical. This is studied in detail in 270, and probably you have touched upon it a little bit in 170. Again, I will give you here what we need from this theory. Okay, first of all, how do we represent? Like here we talk in terms of transfer function. Look how the theorem is written. It is written in terms of what? Solutions of the denominator. So everything is in terms of the transfer function. Give me numerator and denominator, I tell you everything. Okay, I tell you stability, and if the system is not stable or you don't like the performance, I tell you how to design a controller. Just give me the numerator and denominator. Everything in terms of the language. Here, what is the language? What is the main representation? It's not in terms of transfer function. It's actually in terms of something called state space model. And again, you probably have seen it. What is the state space model? It's a special form of the equation of motion. So whatever form of the equation of motion, please turn it into this form. What is this form? Make all the differential equations first order. So x dot here. So x is a vector, x1 dot, x2 dot. So I have several variables that are differentiated. Get them together, and since it's a linear system, it will be just constant times your x's again plus constant times your inputs. in this theory, the input is usually denoted by U, but we have our own U, right? The forward speed of the airplane. So I'm gonna use here U tilde. So let's see. What are x's again? These are my state variables. The main variables in the system. Like what? Like if I have a DC motor, it will be the position, the velocity of the shaft, and the current of the motor. Like if I have an airplane, it will be the motion variables, U, V, W, P, Q, R, theta, phi, psi. Whatever your system, they are the main variables defining the system. This is physically. Mathematically, they are super easy to identify. They are simply the variables that are differentiated. Whenever you see something differentiated, it is one of the states. So because as you see here, we have to get their derivatives on one side and everything else on the other side. So x's are my state variables. U, like I said, this is the control inputs. So like here, it's our delta elevator. Okay, so please turn in your equation of motion into this form. So let's do that. And again, I will require that you guys know how to do that. So we're gonna do it together. So let's see, theta double dot, here is my equation of motion, minus mq theta dot minus m alpha theta equals m elevator elevator. First of all, you need to identify what is your states, what are your x's, and what is the u. That's easy because, like I said, my x's are really the variables that are differentiated. What do you mean? I mean, if you have here theta dot in front of your eyes, so theta is differentiated. So this means that my first state is theta. That's fine. What else? Anything else differentiated? Yeah, I have theta double dot, which means that theta dot is differentiated. So my second state is actually theta dot, or it's q. We know that theta dot is q, right? So simply, these are my two states. A second order system has two states. A ninth order system has 9 states, and so on and so. Okay. Any question about that? Any question about identifying our states? And the input was easy. The input is really delta elevator. Okay, knowing your equation of motion, the black equation, and the definition that you came up with based on the equation of motion and your knowledge of the physics of the problem. Now, please write it in the green form. That's easy. Let's do it together. So what's the green form? It's d by dt of your state variables, which are theta and q, equals something times your state variables, which are theta and q, plus something times your input, which is delta elevator, right? And let's fill these matrices together. Maybe you can zoom here. Okay. So let's do it together. Let's do the second equation, the second row, because it's a bit easier. Why? Because what is the second row? This is d by dt for q, and we know that q is simply theta dot. So it's d by dt for theta dot. D by dt for theta dot is simply theta double dot. So this guy is theta double dot. So please, from your equation of motion, get theta double dot in one side and the other things in the other side. So here is my theta double dot. Move all these things to the other side. So the other side, I will have m alpha multiplying by theta. So here, m alpha multiplying by theta. I have mq multiplying theta dot, or q, right? What else? I have m elevator multiplying elevator. Any question about filling the second row? The first row is trivial. Why? It's just because I had one equation and I used it already. So the rest is just to, complete this format. What's the first row? It's d by dt for theta. So it's theta dot. Please write theta dot in terms of theta, q, and elevator. Well, theta dot is actually q. So it's 1 times q and 0 otherwise. So that was trivial. Just to complete the thing. Any questions so far? So now
Professor,
my
could you repeat that?
yeah, of course.
So what is that? 0 and
Any
1?
first of all, any issue with the second row?
Professor, I mean, I understand it, I think. I'm curious, why use Q instead of theta dot in this case? Why not just use all in terms
That's
of...
perfectly fine, right? They are equal, right? I'm just
Right.
trying to prevent confusion. You can very legitimately replace Q with theta dot. That's fine.
Okay, okay.
That's perfectly fine. It is just trying to prevent confusion, but it's perfectly fine. Frankly speaking, strictly speaking, we don't write actually theta and q anymore. We should write x1, x2, x1, x2. Okay, if we like. So okay, we filled already the second row because this supposed to be easy or straightforward. Why? Because I'm using my only equation of motion to fill the second row, and I ran out of the equations. I had one equation, I used it. What is the first row then? How should I fill it? Is actually you fill it using the definitions of your states. Look at this form. This form asks you or forces you to write down the dots of your states in terms of your states x and your input, nothing more. So try to do that. Try to write down your dots in terms of your states and your input. Okay, what's my first state is theta. So its dot is theta dot. Please write theta dot as a linear combination of your states, theta and q, and the input. Well, theta dot has nothing to do with the input, so it's 0. Theta dot is actually simply q, right? So it's 1 times q and 0 times theta, 0 times elevator. Question about that? So I require that you, given an equation of motion like this black one, you can go classical and get the transfer function, or you can go between quotation marks modern and do the state space model. This is my state space model. Why? Because now I have here the left hand side is my x dot. This is my A matrix. This is my x. This is my B matrix. And this is my U tilde, the input. So I managed to exactly write my equation of motion, the black one, exactly on the form of state space model. Okay. Why do you write it on state space model? Because this is the language that is being considered here. If everything in the classical is in terms of transfer function, everything here is in terms of the matrices A and B. Like here, any system, when you consider a system, I really don't care if this system comes from an airplane, submarine, or an oven. I really don't care. Give me the numerator and denominator. This is sufficient information. I'll give you stability and I'll tell you how to design a controller. Exactly the same here. I don't care if this A and B pair of matrices came from an airplane or came from anything else. Here is the stability, which I'm gonna show you in a minute, and here is how to design a controller. So an airplane compared to another, they differ in A and B, okay? So theorem. What is your theorem here? I mean, we expect the theorem here was in terms of your language, the transfer function. So it was really in terms of the poles. Here, the theorem would be in terms of the A and B matrices. So it tells you, here is the theorem. State space model is stable. Again, we have the luxury of if and only if conditions because it's a linear system. If and only if all can be poles anymore, because poles of transfer function, we don't have transfer function here. All eigenvalues of the matrix A. You have to give it to me in terms of A and B. Eigenvalues of A, the same criteria, lie in the left half plane. So let's have the example. let's have the example. Our example, the state space model. We already got it here. So my A matrix was 0, 1, M alpha MQ. This is my A matrix. Let's get the eigenvalues, please. How do you get the eigenvalues? The eigenvalues always is the determinant of lambda I minus A equals 0. So let's get it together. So how do you get lambda I minus A? That's easy, actually. Let's get minus A first. So copy all these things with minus sign. So I have -1, I have minus M alpha, minus MQ, everything with my minus sign. And then add lambda I, add lambdas over the diagonal. So this is lambda, lambda, that's it. That's easy. Then get the determinant, please. So the determinant, as if you remember, this times that minus the other way around. So lambda squared minus MQ lambda minus the other way around, so minus M alpha equated to 0. Solve for lambdas. These are your eigenvalues. And for stability, the eigenvalues, they all should be in the left half plane. So this is the equation that I'm going to solve for the lambdas. Let's record the characteristic equation. This was the characteristic equation that I got from the transfer function. It was S squared, here it is, S squared minus MQS minus M alpha, and I'm solving for the S. This is my characteristic equation. So actually it is exactly the same. It is exactly the same. So my characteristic equation how do I get it? I get it if I have a transfer function, it's just the denominator equals 0. If I have a state space model, it's the lambda I minus A equals 0. And in either case, it's exactly the same. Here, in the language transfer function, gives you the poles, which determine stability. In the language of state space models, it gives you the eigenvalues of the A matrix, which determine stability. In other words, the eigenvalues of the A matrix are exactly the same as the poles. So this is the eigenvalues of A are exactly the same as the poles of your transfer function. Okay. You stressed, or I actually stressed, the importance of these mathematical objects, poles of transfer function, eigenvalues of A, like so much. Why? I mean, we love to have some physical meaning. Why we're stressing this so much? So first of all, I need to make sure I'm going to discuss their physical importance in a minute, but I want to make sure first, given an equation of motion like this, black one, you can get the transfer function and you can get the state space model. Any question about that? All right. So let's see. I mean, we making a big deal here of these, but they are mathematical objects. I mean, at the end of the day, yes, but so let's see. I mean, we know a priori now that they determine stability, right? If they are in the left half plane, then the system is stable. If they are in the right, then if any of them is in the right, then the system is unstable. If you touch it, it will blow up. That's correct. Okay. But is there more? Yeah, of course, there is more. Let's consider this, because this is very important. And please pay attention here. And again, it's a review of 170. So let's see. And let's do it for a second order system. So the characteristic equation is S squared plus something, right? Something times S plus some free term. We usually, in a second order system, we usually like to call the free term as omega n squared, your natural frequency. And we like to call the coefficient of S 2 zeta omega n. So now on, if I give you if I give you any characteristic equation, you should be able to identify your omega and look at this again. My M alpha is really the natural frequency. My MQ gives you the damping zeta. Okay, fine. So this is my characteristic equation. Okay, so this is the S domain. So this is the real and imaginary. Because I'm going to solve this quadratic equation in S to get the poles, right? Whether you call it poles of the transfer function or eigenvalues of A, it doesn't matter. They're exactly the same and they are determining stability. They should be in the left here. And let me go 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5. So second order system, two poles. Why we're obsessed with the locations of the poles or with the poles in general? Because of the following. This distance actually, why this is, did I do something wrong? Okay. So this distance, the horizontal distance is actually zeta omega n. And by the way, zeta, I accept anything from you. Do anything, okay? Do anything, this is zeta, whatever. So the horizontal, the real part of the poles is the multiplication zeta times omega n. And the diagonal here is omega n, okay? So give me the location of your poles. I immediately give you the natural frequency and the damping zeta. Good, but is there anything more? Of course. Now we're going to the real thing, because we don't like the S domain, right? This is the S domain. It's a fictitious domain. We like what? We like the time domain. It's a real, we see it. And this is the output of my system. Like in the airplane, this is my theta of the airplane, pitching angle of the airplane. The pilot gave a command, the stick, pull the stick towards him or her. So the airplane will pitch up. And the theta will change, say, from 0 to, say, the pilot will give a command 5 degrees. This is 5 degrees at the end of the day. Theta will do something like this. Okay. So from the moment the pilot gave the command here to the moment theta attains this value that the pilot hoped for, any system, in particular the airplane, will take some time, and we call it very expressively the settling time. It's a very important thing to characterize the performance, because if it's 1 hour for an airplane, it will not be satisfactory. It will be crazy, right? So the settling time is simply 4 divided by zeta omega n. Give me this real part of the poles. I immediately give you how many seconds this airplane or this submarine will take until it settles after it gets a command. It's a very important characteristic, right? So the location of the poles now, they are not just mathematical objects or fictitious things or merely determine stability. No, they determine the performance, how things will behave. Not only that, this thing. So if this is 1, I will just erase this now, because we always represent it in terms of percentage of this value. So let's assume that this is 1, unity. Now, if this is unity, this is something what we call, or what you guys called in 170 as percentage overshoot. This is e to the negative pi zeta divided by square root 1 minus zeta squared. Everything is in the exponent. So give me zeta only, I immediately give you the percentage overshoot. So remember, here are the location of the poles. I got my poles, fine. My poles determine immediately zeta and omega n. And zeta and omega n, zeta alone determines the overshoot, and they together, they determine the settling time. We feel the settling time. We understand why important it is. It is how fast your system is responding. What about the overshoot? The overshoot is very important in the following sense. because the example that I usually like to give, assume that this is, I'm at landing and this is say 10 degrees. So the pilot gave a command and this is 10 degrees. I'm landing at a relatively high angle of attack because this is what we do on landing. Is there a question here? This is the expression for the percentage overshoot. It is this one, e to the negative pi zeta divided by 1 minus z squared. So if you give me your zeta, I get the percentage overshoot. The percentage overshoot is how much I overshoot beyond the steady state value during my excursion. Okay, so consider this hypothetical situation. I'm giving a command, the pilot's giving a command to 10 degrees, steady state 10 degrees angle of attack. Fine. So I'm doing landing with a relatively large angle of attack, which is typically the case. And the airplane is well designed, so the settling time is fast, like a couple of seconds. Very good. Awesome. So I reach from here to exactly the value that you like in a couple of seconds. But in the middle, during the excursion, I overshoot to say 15 degrees. If you have 50% overshoot, if you computed this and find it 0.5, then this is 50%. So if this is 10, this will be 5 degrees, which means what? I will eventually arrive to 10, but during the excursion, I will touch 15 degrees. And if this is your stall value, then you stall the airplane in the middle. So this is detrimental and catastrophic. So the overshoot is an important thing. Together, they are the main two parameters characterizing your performance. So I know I stress this much, but the end message, the take-home message is these poles or these eigenvalues of the A matrix, which tend to be mathematical objects, they are very physical. Their locations are very important. Why? Because they determine immediately how fast your response and how much you overshoot. These are things that we care about in our performance. Okay, so this is why in the modern control theory, we are obsessed with something called pole placement. We want to place the poles in the location that gives us the desired performance. So we do it actually the other way around. I start with settling time and overshoot. From the overshoot, as you can see from here, I solve and get zeta. Once I have zeta and the settling time, I get omega n. Now I have zeta and omega n, so I get the location of the poles. So these are the desired location of the poles to get me the desired performance. The next step is to, design a controller that places the poles in these locations. This is, you will always see this in model control theory, pole placement. We do pole placement. We place every single pole in the location we want. Any question about that? And sorry for overstressing it.
Professor, I'm curious, are these numbers for instance, settling time and the overshoot, are these an instance where there's sort of like if we're solving a problem, what's a reasonable number to get? At what point is it's sort of considered, reasonable?
That's a very good question, Sam. And for an important system like an airplane, we will not leave it subjective. So there is a whole area of research. I'm going to take one whole lecture about this. Is the topic of flying qualities. It based on opinions of pilots for tens of years. We collected actually the desired locations of the poles that give desired, between quotation marks, desired settling time and overshoot. Okay, so it's not for other systems that are not that important like the airplanes. They're usually coming from experience of the designer. Okay, so this is a very important question. What is, since now or in a minute we will have a very powerful tool in modern control theory that allow us to place the poles wherever desired. Okay, what is desired then, right? So this question will come in one of the later lectures. It's called flying qualities.
Awesome. Okay, looking forward to it. Thank you.
All right.
Professor,
so yes.
Just to kind of piggyback off of Sam's question, does that mean that we don't have, like in 170, there was if you were a certain magnitude away from your first poles, if they were imaginary, that you did not take it into account, that the system would really they would really affect system behavior. Like if you were, you know,
Do you mean if you have a pole here, third pole far away, or
yeah.
Yeah, that's a good point. Typically, we will have more than second order system, right? But we typically care about what we call the dominant poles. The dominant meaning the ones that are closer to the imaginary axis. Particularly if this one is really far away, like 5 times the real part, then it will really not affect the performance. We will care about the dominant ones. And this is a very good point. So thanks for bringing up. I'm coming to it in a minute, actually, because it differentiates the classical control theory from modern control theory. It seems that this lecture will be a bit long, but it's important. I consider this an important lecture. So let's continue. So okay, we got the importance of the poles or eigenvalues. Fine. Now. We studied stability. I mean, stability is so easy. Get me a transfer function, I get the poles, I check if they are in the left half plane, I'm done. But what if the system is unstable? We need to design a controller, right? Do we really encounter scenarios like this in flight, that an airplane is unstable, and why? I mean, we keep adding stabilizing elements. We designed in the first half, we designed a vertical tail, a horizontal tail, a dihedral. Why now we're getting instability? What's the source of this? So let's discuss a couple of things, like need, and we will add more next time. Need for feedback control. It's a nice, interesting example. Let's see. So this is the fuselage reference line, the x-axis of the airplane, okay? And I have here, say in red, this is the aerodynamic center of the wing. And I have the aerodynamic center of the tail somewhere here. And as you guys know, the aerodynamic center of the entire airplane is somewhere in between. It's the average, actually, but it's weighted average. It's more towards the wing because the wing is bigger. So this is maybe the aerodynamic center of the airplane, which we call what? Anybody remembers? We call
The
what?
neutral point.
The neutral point. Very good. Okay, and we want the CG to be in front of the neutral point or behind for stability. Any suggestions?
Towards the wings, right? Towards the nose.
Exactly. Very good. So this is my CG for a stable configuration. And we have been obsessed with this distance. This is, if you remember, this is the static margin, HN multiplying by C bar. Very good. So if the CG is in front of the neutral point, the airplane is stable. But remember, if it's too far from the neutral point, the airplane is too heavy. Okay? Fine. Now, I'm recalling that for subsonic that we studied in the beginning of this class, the aerodynamic center is around what point? Do you remember? Anybody remembers? Quarter core, very good. For supersonic that we did not study, the aerodynamic center actually moves to half chord, which is quite interesting. So this means that I have an airplane that is designed to be supersonic. Okay, but it doesn't fly supersonic all the time because it has to take off and land. So it goes subsonic for a while. So at the beginning, this was the configuration. Now my aerodynamic centers, all the aerodynamic centers will move backward. So this guy will move backward here. This guy will move back. Oops, come on, man, what happens? Okay. So this guy will move backward there. Fine. And consequently, the green thing for the entire airplane, because it's simply the weighted average, will also move accordingly, will become here, which means that in the supersonic, this will be my static margin. So what's the problem with that? The problem is now in the supersonic regime. So usually supersonic means it's a fighter airplane, right? Usually. So it's a fighter airplane, and its operating point in the supersonic. This is the operating point. I have too large static margin, which means too heavy stability. Which means what? Which means the airplane is heavily resisting disturbance. Remember, the airplane will not distinguish between a disturbance coming from the surrounding air, which is an actual disturbance, versus a pilot command, right? The airplane will not distinguish. It will resist both in the same manner. So this is not acceptable, that a fighter airplane, which is supposed to be maneuverable, that in its operating condition, the supersonic, it becomes crippling to the pilot, right? So what's the solution? Well, the solution is, let's move this guy here so that in the supersonic regime, it's that small and acceptable static margin. But this means what? This means that in the subsonic regime, it is unstable. And it's a typical scenario. F-16 is really unstable in the subsonic regime. It's too unstable, actually, F-16, to the extent that so one time there was a what do you say, an exhibition in a conference or something, and then let me do what? Okay. Anyway, so there was an exhibition and in a conference, and then there was a booth for the General Dynamics guys of F-16, and there was another booth for Boeing. Boeing designed the ejection seat of the F-16. So the issue is they were bragging, the Boeing guys, they were bragging of how many times the F-16 ejection seat were really ejected in flight, and all of them were safe, and so they were bragging about their ejection seat, but this ejection seat means a bad thing for the for the General Dynamics airplane. It means that we're losing the airplane. So that was quite interesting. So yes, F-16 is too damn unstable of an airplane. If it's flight computer, you can't fly it as a pilot, so it has to be flown automatically using a feedback control system, using a flight controller. So if anything goes wrong with the flight computer, I mean, there is no hope to recover the airplane. So you have to eject and go.
Professor, under what circumstances would that even happen? Like, how can the plane just fall out this?
Malfunction of a sensor, for example. This is the worst thing, right? Like what? Remember the accident of the 737-800, right? This is all because of a malfunction of a sensor, and the solution was simple: disengage the autopilot and fly it manually. But in this case, for an F-16, you can't do that, right? Because if you disengage the autopilot, it's too unstable. You would not be able to fly it manually. So you have to do ejection seat. Okay, another thing which is related. I know that it's a long lecture. So what else? A very related thing. So if this is my airplane, and remember the x-axis starts somewhere here. I'm gonna sketch a diagram. So this is the XCG, okay, versus the drag at balance. It actually turns out that it changes the CG. Why? Because balance requires that you deploy the elevators, right, to achieve balance, of course. And this depends on the CG location. How far your elevator from the CG? All right. So as usual, I'm going to put here the neutral point because you guys know that the neutral point is the limit. CG behind the neutral point is unstable. In front of the neutral point is stable. Too far away from the neutral point in front means too heavy stability. Okay, so this is the variation. So I don't want to imply that this is zero. So yeah, all what I'm trying to say is that the drag for balance attains its minimum at a location that is, what is this location? What do you know about this location? If your CG is here. Anyone can tell? If the CG is here, what do you know about?
It's unstable.
It's unstable. It's behind the neutral point. And this is a typical behavior, by the way. The drag attains its minimum, the drag for balance attains its minimum at an unstable condition. So this is a clear contradiction between performance and stability. We always see this contradiction. You want performance, you want to minimize drag, you want higher lift, you want higher lift to drag ratio, then we sacrifice stability. So how to regain stability? Well, design a feedback controller. We don't get it naturally from the airplane. Design a feedback controller. So that's enough, right, for motivation. Let's go and design feedback controller. How do feedback controller? I have here theta double dot minus mq theta dot minus m alpha theta equals m elevator elevator. Okay, so assume that this is my equation of motion. I don't have enough stiffness and don't have enough damping. I don't have a horizontal tail at all. And I want to do feedback control. I want to play with my elevator in a smart way so that the end result, my airplane behaves as if it has a large enough horizontal tail. So I'm saving actually area of horizontal tail by doing smart feedback control. How can I do that? That's easy. My elevator, I'm gonna write it as follows. The elevator has several contributions. Let me do that. Let me write it here. So my elevator, I'll write it as some elevator trim for balance. Remember the one that we calculated in the very first half of the course, and some value, 3 degrees, 5 degrees elevator for balance. Okay, at cruise. And then there is something coming from the pilot, command to do a maneuver or something. In general, maybe 0 for cruise, maybe not. Plus the delta elevator that we're gonna use for feedback. Can you tell me what is this delta elevator? Well, okay, let's see. You wanna do damping, so you wanna achieve pitching moment that is proportional to theta dot, right? Fine, so actually I'm gonna do the following. I'm gonna, my delta elevator for control, I will have it as a term that is multiplying theta and a term that is multiplying theta dot. It's as if generating an effect that is proportional to theta, generating an effect that is proportional to theta dot. Artificial stiffness and artificial damping. Let's please substitute this delta elevator all the way here. So, and collect terms together. So I will have theta double dot minus mq plus k2, I'm sorry. So this guy will multiply by m delta elevator. I have m delta elevator here times k2. This is all multiplying theta dot. I'm just collecting the terms multiplying theta dot all together. And terms multiplying theta all together. So this was m alpha and m delta elevator times k1. This is all multiplying theta. Now it's m elevator times delta elevator naught. I'm gonna collect this 2 and write it as delta elevator naught. So look at this equation now. At the beginning, I started with some stiffness and some damping. Now I augmented this stiffness and this damping. I can really adjust my K1 so that the total effective stiffness is what I want. I can adjust my K2 offline so that the total damping is what I want. So this is how we design it. I will give you a more principled way to design it. But this is just an intuitive way to design your gains. How we implement it in flight. That's also easy. So let me have, do you have something here? Okay, that's fine. This is my elevator. And there is a servo here that moves your elevator, right? Okay. All what I need is to apply this equation for my delta elevator. This is all what I need. So there is some value coming from the trim. I'm gonna sum many contributions. Delta elevator trim, this is coming from your computer. You compute it like we did exactly in the first half. Fine. There is another one coming from the pilot. So here is the pilot, whatever. Command, right? Coming from the stick of the pilot. What else? The change due to feedback control. This is a term multiplying by theta and term multiplying by theta dot. Here, where it's now clear that I need to put sensors to measure theta and theta dot. So I'm gonna put a gyro here. Luckily, it will give me theta and theta dot. Please. All right. Or Q. You design gains offline. This is times K1. This is times K2. The result, feedback, all of them here. This gives you the right amount of delta elevator that should go to your elevator to adjust the airplane. And this loop runs continuously during flight. Whenever the airplane gets a disturbance from outside, it will reject it. Whenever the airplane gets a command from the pilot, it will execute it. And it's with what? With the right settling time and overshoot that you design these gains to meet. Any question about this implementation? Any question? The last thing I will give in this lecture is, okay, how to do it? How to do pole placement? If I have settling time and overshoot desired, and I have some system, I have A and B matrices, how can I do it? So this is actually goes back to, but let me, I know that the lecture is a bit heavy, but so let me first, if you have any questions so far, folks, please, any questions?
I have a question.
Yep, go ahead.
Can you explain one more time how it becomes unstable going from supersonic to subsonic again?
Yeah, very good. It's not, so that's good. So let's see. I'm saying if you design the airplane to be stable at subsonic, so this is the CG at subsonic, okay? And this is the neutral point, the green one here. The green one is the neutral point or aerodynamic center at subsonic. This configuration, CG is in front of the neutral point, is stable. So it's stable in the subsonic. What will happen? It will be too heavy stability in the supersonic because this guy moves backwards simply.
Yeah.
So what is the solution? I cannot tolerate that. I cannot tolerate it to have my fighter airplane at its operating condition, which is supposed to operate at the supersonic operating condition, to be too heavy stable. So I cannot tolerate that. So what is the solution? The solution is that I'm going to design it to be unstable, actually. So this is my CG. The pink one is my CG. I'm going to design it to be unstable in the subsonic, because now it's behind the aerodynamic center.
Oh, I see.
But now in the supersonic, it will have the right amount of stability.
Oh, okay.
Yeah.
Thank you.
Mm-hmm.
Professor?
Yes.
I was wondering, like, for how you go from subsonic to supersonic, how do you physically change the distances for the aerodynamic centers?
No, this is
or is it only designed for one of those conditions?
what I don't get the question. So let's see. What's the question again?
Or you know how? Oh, never mind. Okay, I was just confused.
No, that's fine. That's fine. So let's
Because
think
I was
together.
all-
Let's think out loud. That's fine. What is making you confused?
So when you drew the arrows from the original aerodynamic centers for the wing and the tail, and then you shifted them back, I thought it was something you'd like physically do to the plane.
No, it's aerodynamics. So it's coming from the air, and this is just physics of the air. Turns out if you're flying subsonic, the physics of the air gives you your neutral point at quarter chord, but the physics of the air changes from subsonic to supersonic. And you have no control over this because this is really the physics of the air, how much the air is responding to your motion, right? It's like the CL is 2 pi alpha. This is really the physics of the air. You have no control over.
Yeah, okay, yeah. I had no idea how you would physically do that in the moment, so I was very confused.
Yeah.
Thank you.
You're welcome. So let's do pole placement. One thing that I like to emphasize, and it is related to Jeremy's previous question. What is unique about this modern control theory, and why do I need to learn a new language? And so this was pretty efficient and perhaps sufficient in many examples. Indeed, the classical controller here, if you guys remember, was the PID. This is like 90% of actually even flight control systems on conventional airplanes, they are PIDs, and 90% of even more than that in industry, other than aerospace, they are PIDs simply. And people get to blame the control theoreticians. The control theoreticians for making things complicated. Every PID works fine. Yeah, that's right. The point is, let me give you the following example. So we have a Boeing 747, so it's a huge airplane, and we want to design a control system. Remember, the airplane has 9 states: U, V, W, P, Q, R, theta, phi, psi. 9 states. So it's 9-order system. If I write a transfer function, I will have here S to the 9 or S to the 8. It depends. It's between 8 and 9. Okay. So it's 8th or 9th order system, and I want to design it to achieve the following performance: settling time ½ second, and overshoot 0 overshoot. So first of all, this is a crazy desired response, and it's not physical, and a huge airplane like 747 will never be able to do it. But aside from the practicality of it, can you at least theoretically design a control that does that? Well, frankly speaking, I can't in the classical control theory. Using a PID or any of the controllers that we learn in the classical control theory, I cannot guarantee that I will achieve this performance, theoretically at least. Whereas here, I am always guaranteed to give you whatever performance you like, whatever performance you dream of, at least theoretically. There are practical limitations. Why you're guaranteed to at least theoretically give me what I dream of? Because I simply place the poles, all the poles, the 9 poles of the airplane, I place them all together at the place I like. Whatever places I like, I will place them there. In the PID, you're using 3 gains, P, I, and D. So you will have authority to place 3 poles. If you want to speak this language and do pole placement, you will place 3 poles. But the rest 6 poles, they will go to locations where you don't have any control over. Okay, so theoretically speaking, you cannot not achieve this very superior and vigorous performance using this classical control theory. But in modern control theory, you'll be able to achieve it with a price, and we'll know the price right now. So here is the pole placement. We have our system, it's x dot equals, It's exactly the analog of that. Here we're feeding back by what? Remember, by the way, we're always interested in what we call here. This is what we call our control law. The law that governs your controller, your input. Because all what I need in this control design is how much input should I give at each second? How much input should I give at each instant to stabilize this airplane? If you give me, if just someone magically gives me, okay, at this instant give 2 degrees elevator, next instant 2.5, next instant -3 degrees elevator, okay, I'm fine. Just give me how much elevator should I give at each instant, and I'm done. The power of this theory is that it gives you an equation where just you substitute at each instant and give the right amount of delta elevator, and it works universally, right? It works perfectly well continuously with flying. Very good. This equation, magic equation, what we call control law. You remember what form of the control law, what form of controller is this from your classical 170? Something times your output plus something times the derivative of your output. What's that? Exactly, it's a PD. It's a PD controller. So this is a PD controller. So in the modern control theory, it tells you, okay, why not feeding back only by the output derivative and output integral in the case of I controller? Why not feeding back by all your variables or your states? So I have, where should I put it? Maybe it's here, okay. So this is my system. And this is your input. It usually comes from an actuator. Oops, this is bad, right? Actuator. And I need just how much should I give here? Well, feedback, but by all your states. So we write it as the control law. The control law we write it as negative K1 x1, K2 x2, Kn xn. So we write it actually as here K1 rows times x1 up to xn, or in a matrix form, it's just some K matrix times the x's. So please measure your first state. Put a sensor to measure your first state, x1. Put a sensor to measure your second state, and so, xn. And each one of these multiply by the gain that you designed offline. Add them all together in negative feedback, in addition to the command. The result will give you the magic right amount of input that will stabilize the system. Not only stabilize, it will give you the performance that you like. Very good. What is the price that we're paying? Well, it's too many sensors. If we have 9, we're fine with our PID, just three sensors at most. Here, if it's a 9th order system, we need 9 sensors, and each sensor, some sensors are costly, some sensors are noisy, and you do lots of effort to filter them out, right? But what's the gain? The gain is that theoretically I can achieve whatever performance dreamed of, right? I can place all the poles in arbitrary locations, whatever you like. Okay, how to do it theoretically? Let's have an example, quick example. Remember, this is x dot equals ax plus bu. This is your system. Simply substitute this guy from here to there. Okay. When we do that, I have x dot now equals ax, but also there is something times x here. It's minus bk, all multiplying x. So x dot equals something times x. This must be my new A matrix, or what we call closed loop CL. This is after closing the loop. Before the feedback, my A matrix is the one that gives me stability. If I don't like it, I do feedback control. And now I have a new A matrix after closing the loop. This new A matrix is what? Is the old one minus BK. So I can simply design my K's, gains here, to adjust the closed loop matrix. Example, quick example to finish and go home.
Professor?
Yes.
I apologize, but the B matrix, what was it again? Is that, I don't remember.
No, that's fine. This is the standard form that we should have something multiplying the x's and something multiplying the input. So here, for example, our B matrix is 0 and M delta elevator. It's whatever multiplying the input in your equations of motion. This is the B. A is the relation between the states and each other. B is the relation between the states and the input. U tilde is the input, okay? $6.48, let me give you this quick. Example, A matrix that, or here is, actually I have it here, let me, oopsies. This is your system, and it is desired to achieve settling time 4 seconds and percentage overshoot 4.5%. All right. So from these two, this thing I equate it with e to the negative pi zeta over square root 1 minus zeta squared. I solve it for zeta and I get zeta. This will be 0.707 or 1 over square root 2. Okay. Then settling time now is 4 divided by zeta omega n, and this is 4, so I can solve for omega n. It is square root 2. I can now write down my desired characteristic equation. What is that? It's s squared plus 2 zeta omega ns plus omega n squared. So it's s squared plus 2s plus 2. This is the one that I hope for. Okay. What is your A closed loop? My A closed loop is A minus BK from here. So my A matrix, here is your A matrix, 0, 1, negative 2, negative 3. Minus B, here is your B matrix, 0, 2, times K. K are gains, so it's just K1, K2. And please, please, please do this. Do this on a slow pace because it's so trivial that people always get confused and do it wrong. Because it's a column by a row, so the end result is actually a 2 by 2 matrix. 0 times K1 is 0, 0 times K2 is 0, 2 times K1 is 2K1, 2K2. And now subtract this guy minus the black matrix. So I get, oopsies. So I get here 0 minus 0, 1 minus 0, negative 2, negative 2K1, negative 3, negative 2K2. This is your A closed loop. So this is the one that gives you the characteristic equation and the poles. How you do it? Lambda I minus A closed loop. So this is minus A closed loop first. It is minus 1, 3 plus 2K2, 2 plus 2K1. This is the minuses. And then put lambdas over the diagonal. Lambda, lambda plus. So this is 0. Multiply. So lambda squared, this by that, minus the other way around. Minus, minus. So this is plus. This is 0. This is your characteristic equation. the closed loop characteristic equation. Compare it with the desired characteristic equation. So this is compare versus s squared plus 2s plus 2. Compare the coefficients. So this gives you k1 is 0. This gives you k2 is negative half. Okay, so this is how we do pole placement to get the gains. Of course, noting that k1 is 0 is very useful. Why? Because if a gain is 0, it means this state is irrelevant, which means that you can completely get rid of its sensor. You don't need it. Good. And so the final result here is the control law. What's the control law? The control law is my input will be negative k1 x1, which is 0, negative k2 x2. So this is my control law. Feedback by the second state, always multiply by half. This is the right amount of input to give you the 4-second settling time and 4.5% overshoot. All right, guys. Questions? I'm done for today, and sorry for getting over time, 3 minutes or something. Questions? Let's see.
Can you scroll down?
Just a sec. There was what? Homework 7 is due next Thursday. So, by the way, the homework was due tonight, right? At midnight, correct? The homework 6.
Yes.
Yeah, I'm extending one day, so it will be tomorrow midnight. I'm gonna send that. Okay. There was a question here. Was a question? No.
Professor. Sorry, go ahead.
No, you can go ahead. It's okay.
I was going to ask about the homework, so if you want to ask about the lecture, by all means, go for it.
No, it's okay. Go.
Okay. Professor, I was going to ask about homework 6, if that's all right.
Mm-hmm.
Okay. Problem 2.
Okay.
I did it 2 ways, and I also spoke with the TA regarding it. I'm winding up with an integral that is c as a function of y times y cubed, and I'm just wondering whether that should be y cubed. We didn't see y cubed appear before in any of the examples.
Let me see if this is really the case. Y cubed. This is CNP, right? Yeah. No, frankly speaking, what is the source of y cubed?
So we have delta alpha wing, which is py over u naught.
Very good. So this is 1y. Okay.
Yep.
And
then when I wrote out the yawing moment, the differential form dn, the moment arm is y. So
that's right. So this is y squared.
Y.
This is y squared. Very good.
And then the third y came from the TA said to include the sign of, because the lift vector is tilted forward on the right wing and backward on the left wing, to include the sign of that angle. So you're just looking at the x component of the lift.
That's right. But so let's okay. And I admit, guys, that this homework is a bit hard, but it's I mean, the first and third problem, they are not that hard, frankly speaking. I mean, anyway. So let me tell you, you have L note here. It's not straightforward in the sense I have left, sine, and angle. I agree. Okay, but this lift is what? This should be the total lift force. So it's L naught plus delta L on one wing and minus delta L on one wing. Okay, let's focus on one wing first. So it's L naught plus delta L, for example. Okay, multiplying sine the change in the angle, sine delta alpha. Okay.
Right.
Okay. So now So L naught plus delta L, this is two terms, each multiplying sine delta alpha. So I have L naught times sine delta alpha plus delta L multiplying sine delta alpha. Here, where it is delta times delta's higher order terms, this term is neglected. And you remain with L naught, the left at the operating, right? L naught multiplying sine delta. So the sine delta alpha gives you the y. L naught doesn't have any y in it.
Oh, okay.
So you still have y squared. There's no y cube.
Okay.
Questions, folks?
So is L not Q C of y dy times little CL alpha wing?
Actually, not CL alpha, little CL wing, right? The operating
Okay.
total CL is exactly. It's not CL alpha now. Yeah.
Okay.
Mhm.
Okay, I think that clears it up. Thank you.
You're welcome. Yeah, this is the only subtle point in it. Yeah. Other than that, it should be straightforward. Questions? Abdullah, you had a question, I guess.
I was gonna ask if we had a quiz, but I'm assuming
We
you
don't have. I mean, that's a tiring lecture. I would be torturing you. I intended to give a quiz, but it seems not possible. Okay.
Thank you.
All right. Questions, folks? See you Tuesday, and the homework is extended one day. Good luck.
Thank you, Professor.
You're welcome, Manuel. Bye-bye. Bye, everyone. Jesus, Sophia, Michael, Jessica, Dorian.